Okay, so all right, so we're recording there. All right, so go ahead, Daniel, and go ahead and ask your question.
Yeah,
So it's from this homework, I hope, the chain rule homework.
yeah, the chain rule homework.
Yeah, let
Can
me
we
open
do
that one.
question
Yeah,
question 10 and 14?
question 10 and 14. All right, so let me scroll down there. So, I hope I can do this one because I haven't thought about this. Okay, so let's see. Find the slope of the graph of the function at the given point. And then it says use a graphing utility to confirm your results, but you don't have to really do that. Okay, you can do this just with pencil and paper. Um, and so our function there is the fifth root. So we don't often deal with fifth roots, but anyway, it's in my version, it's the fifth root of 3x cubed plus 4x, and we want to find the slope of the graph at the point 2, 2, right? So the slope of the graph means the slope of the tangent line to the graph, right? Okay, because remember, functions that aren't linear functions don't really have slopes. So we use the slope of the tangent line and talk about that as being the slope of the graph. Okay, so what really trying to do here is find the slope of the tangent line. But remember, slopes of tangent lines mean derivative, right? So we have to find the derivative of this function, and we have to evaluate that derivative at x equals 2. The y coordinate here is kind of meaningless to us. We would use that if they were asking us to find the equation for the tangent line at this point, but we're not asked for the equation for the tangent line, just the slope of the tangent line. So all we need is just the x coordinate here at this point, which is 2, but we do need the derivative. So we need to compute that derivative. So let's see if we can do that. Let me see if I can find some blank paper here, and so we can do this. Let me add an extra sheet here to these notes. Okay, and so let's see. That function was the fifth root. I remember that, but I can't remember the rest of it. 3x something or other. So let me look back here. 3x cubed plus 4x, right? And in my version of the problem. But your version might be slightly different. So we're looking for y prime here. That's one way to denote the derivative. Or remember, you can also denote the derivative as dy over dx, right? But those mean the same thing. All right, so this is just a matter of applying our differentiation rules and finding the derivative, and then evaluating them at x equals 2, because that was the point where we were trying to find the slope of the graph, right? Now, in order to apply the differentiation rules, first we're going to convert this, as we normally do, right, from a radical to a fractional exponent. So I'm going to write this as 3x cubed plus 4x to a power, and since this is fifth root, this would be the 1/5 power, right? Okay, so that's very important, especially on the test. Be sure that you convert your radicals, right, back to fractional exponents, because you really can't apply any of our differentiation rules with radicals, correct? Okay, all right, and so now let's go through the differentiation process here to find y prime. Well, of course, you're just going, the whole purpose of taking that radical and converting it back to that fractional exponent is so that we can use the power rule, correct? Right? So our first step in differentiating here is going to be to apply the power rule. So we'll bring the 1/5 down, right? Of course. And so we have 1/5 times 3x cubed plus 4x. And then you have to subtract 1 from that 1/5. That's a little bit messy, but we have to do that. And so that's really the power rule. And once you've subtracted the 1 from the exponent, you're really finished with the power rule. Except here's the catch, right? This is why this problem is in the chain rule homework. It's, you don't have just x raised to a power here, right? You have this expression involving x. It's more complicated than x. It's 3x cubed plus 4x. So to finish this derivative correctly, you have to, at the end, multiply in the derivative of your expression that's raised to a power. If that was just x raised to a power, you wouldn't have to multiply in the derivative. Actually, you could think of multiplying in the derivative because the derivative of x is 1. So you could think of multiplying in 1. That's kind of useless though, right? But here, since your expression raised to the power, the base of your power is not x, right? It's this more complicated formula involving x, then it really is crucial that you multiply in the derivative, which is, let's see, what's the derivative of 3x cubed plus 4x? Well, we're going to apply the power rule again, right? So we're going to bring the 3 down times, bring this 3 down times this 3. So you'll get 9x and then subtract 1. So that would be x squared. And then the derivative of 4x is 4. Remember, whenever you have just a constant times x, the derivative will just be the constant. That is actually also the power rule. That's actually also the power rule. Forgot what I was going to erase there. So in a sense, you're finished at this point because that is an expression for the derivative. But you can simplify this a little bit better. You can simplify this a little bit better if you like. And so let's see. This would be 1/5, and then 3x cubed plus 4x to the 1/5 minus 1 is minus 4/5 times the 9x squared plus 4. If you want to deal with the negative exponent now, you can by taking the reciprocal. So you can write this as, keep the 1/5 in front, and then you can write this as 3x cubed, I'm sorry, 1 over 3x cubed plus 4x to the positive 4/5 power times the 9x squared plus 4. And now you can convert this back to a radical if you like, okay? So you would have 1/5 times 1 over, so 4/5 power means the 5 in the denominator means this is going to be a 5th root again. So we started with the 5th root. We're going to end up with a 5th root derivative, okay? And then you keep the 3x cubed plus 4x raised to the 4th power. So the 4 here in the numerator of that fraction is going to stay as an exponent. So you get an ugly looking thing here, 1 over the 5th root of 3x cubed plus 4x to the 4th power. And then again, times, don't forget, hanging around here is the 9x squared plus 4. I guess you can now multiply all these things together and you end up with 9x squared plus 4 in the numerator, because you have 1 times 1 times 9x squared plus 4. And then in the denominator, you still have this ugly 5th root. So you have the 5th root of 3x cubed plus 4x raised to the 4th power. And that's the derivative now that you're going to use to find the slope of the curve, also known as the slope of the tangent line, right? So let's see, we needed to do that at what? X equals 2, right? So I'm going to evaluate the derivative y prime at x equals 2. Here's how you can denote that with function notation. You can write y prime of 2, or you can write dy over dx, the old style, and then a vertical bar, x equals 2. These two things mean the same thing. I'm going to evaluate this derivative when x is equal to 2. Well, that's going to take you a little bit of arithmetic, okay? Because you're going to have to substitute the 2 for the x. So that's why in the homework they were suggesting, you need to use a calculator and you need to estimate this to 3 decimal places. Let's see. Wow, let's see if well, I'm not sure I want to do this now, but because that's going to take a little while just to do the arithmetic. But see, so all you're going to do here is plug 2 in for x, right? In this expression, and then use your calculator to simplify this. Daniel, does that sort of make it clear how you do that, or was it the arithmetic that was causing you trouble?
Yeah, that makes sense. I forgot to put the x in back and to calculate it, so That was the thing I was missing.
You didn't do what?
I didn't put the x after I finished for the second derivatives.
You didn't
The
put
value of the x
you
value,
didn't put this, or
the x value. Yeah, I didn't put the 2 in.
oh, I see. You didn't put the 2 in afterwards to actually calculate the numerical value.
Yeah, that's
Oh, okay. One thing that, well, so most of that arithmetic is pretty easy when you put the 2 in. The numbers are going to be kind of big though. But you can do that with the calculator. The one thing that might be a little tricky is how do you compute the fifth root of a number on your calculator, right? So, because we don't often compute fifth roots, but you can compute a fifth root by, if you want to compute the fifth root of a number on your calculator, say the number is a, you can raise that to the 1/5 power. That's the same as computing a fifth root. And 1/5 is 0.2. So you could take any number that you want to compute the fifth root and raise it to the 0.2 power on your calculator, not the 2 power, that's squaring, but the 0.2 power would be fifth root. And that's how you can calculate a fifth root easily on your calculator if that's causing you issues. Okay. So the key lesson in this problem is not the arithmetic so much, it's the remembering to use the chain rule when you're calculating the derivative of this ugly fifth root, right? So there's certainly problems like that on the sample test, and of course there are going to be problems like that on the test. So that would be one of our more complicated derivatives to compute on the test. All right, because this involves the power rule and converting radicals to exponents and the chain rule. Okay, so a lot of stuff is going on in computing this derivative. Now, so just a brief aside here before we have another problem, Daniel, but we'll look at that. So the test, right, is a week from today. The test is on the 13th. So people were asking me before class about the review sheet. So the review sheet is ready. The test review has already been posted, right? That's already posted on Blackboard. But the answers to the review sheet is what I need. Those are ready. So I think the link will become available tomorrow at noon. So tomorrow at noon, that's when the answers to the review will appear in Blackboard. Okay, and I will tape a video and go over not every problem on that review, but certain problems on that review. So I'm not sure when that video will be ready, but as soon as that's ready, I will. Hopefully, it will be by Thursday, so I can tell you during class. But when it is ready, I will. If it's after Thursday, I'll email you and let you know. Okay, so I will tape a video. Now, Madison will also still be having review sessions, her normal review sessions before the test. So you can certainly ask about the test review there. So she has a review session Thursday at 9 a.m. And then that's her, is it 9 a.m., Madison? 9 a.m., right?
Oh, yeah, 9 a.m. to 10 a.m. on Thursday.
Yeah, and
then Monday is 12 to 1.
Yeah, Monday is 12 to 1. So those are also great opportunities for asking questions about the test review and other aspects of the test. Remember, the test is going to cover through implicit differentiation, which we're going to finish talking about today. That homework is due on Saturday. I moved that back to Saturday. That homework is due on Saturday. And but the chain rule homework, which Daniel is asking about, that is due tonight. Okay, so you want to finish that by midnight. Okay. All right. So this was problem 10. Let's look at the next problem, 14. Is that the last problem? Not quite, but close. Let's see. So yeah. So
I was just waiting for the water.
go ahead,
I was also watering.
Donna. Were you asking a question?
Oh, I'm so sorry. I didn't realize I was unmuted.
That's okay. All right. So there are problems like this one. not quite as complicated as this one, maybe. Well, maybe. On the test review, something about the test review, it has lots of differentiation problems on it. So there's a big middle section from the test review, which is just a bunch of differentiate this function, differentiate this function. So there's a lot of problems. It's going to seem like, that's a lot for a review, and it is, but you do need a lot of practice with differentiation. It's just something that requires lots of practice. So, try to do as many of those review problems as you can, right? From the test review on differentiation to give you plenty of practice for the test, and of course finish your homework as well. But the homeworks that are covered on the test, again, the last one is implicit differentiation, and that one's due Saturday. So there is time now to prepare for the test, but you need to be working on that, right? You don't want to wait till the last minute. All right, so this is not a conceptually difficult problem, this problem number 14, but it is probably going to be challenging, maybe a little bit challenging algebraically. And so they're kind of warning you about that, actually, because it says use a computer algebra system to verify your results. So a computer algebra system is software that will actually do symbolic calculations for you. In other words, algebra for you, okay? And computer algebra systems will usually calculate derivatives for you. And so they're, encouraging you to check your answer with such a system, okay? So we need to compute the second derivative, and then we need to evaluate it at the input 0, okay? So there are two parts to this problem. We actually have to find the formula for the second derivative, and then we have to, plug x equals 0 into that second derivative formula, all right? And so that's it. It's easy to understand what they're asking us in the problem, but it's maybe harder to carry out. So let's try doing some of this and see how bad it is. So the function is, I forgot it already, something over x plus square root of x plus 4, right? So it's got one of those pesky square roots in it, and that's going to make it more complicated. So 3 over the square root of x plus and we have to evaluate the second derivative at x equals 0. Okay, well, again, before we evaluate the second derivative, we've actually got to compute the formula for the second derivative, right? Okay, so let's see if we can do that, and that means we have to find first, though, the formula for the first derivative, right? So one step at a time here. First, we have to find the first derivative, okay? And so we have to think about what differentiation rules we're going to use to find the first derivative. So this is a quotient. So if you want to, you can use the quotient rule to find the first derivative, okay? So that is a possibility here. Or in this case, though, because this quotient is simple enough, we can rewrite this slightly, and we won't have to use the quotient rule. Let me show you how. First, of course, we have to do this anyway, whether we use the quotient rule or not. We want to take that square root and convert that back to a fractional exponent, right? So I'm going to write that square root as a 1/2 power, right? So square root is 1/2 power. So we would always have to do that, because to calculate derivatives with square roots, we just have to convert them to fractional exponents. But you can also now take this 1/2 power out of the denominator, so you can pull that up so that you don't have a quotient anymore, you don't have a fraction anymore. And the way you do that is by, of course, changing the sign of the exponent. So you can write the 3 over x plus 4 to the 1/2 power as 3 times x plus 4 to the minus 1/2 power, okay? And I think that's useful in this case because, see, you no longer have a quotient now, right? You don't have a quotient any longer. This is a quotient because you have 3 divided by x plus 4 to the 1/2 power. But now here you have it written without a quotient. And so to find the derivative, you don't have to use the quotient rule. And, the quotient rule is, kind of a little bit messy to use and remember, right? Okay. So, so I think there's an advantage here to sort of, circumvent using the quotient. You can't do that always, but in this problem, just because of the way the expression is written, we're able to do that. And now I think it makes the first derivative a lot easier to find, right? Because what can we do here? You're going to use the power rule, right? So bring down the minus 1/2 and then times the 3, and then you have x plus 4 to the minus 1/2 minus 1. So subtract 1 from the minus 1/2. But now, do not forget the chain rule. Look, here you have an expression raised to a power. It's not just x, but it's x plus 4 raised to a power. So to finish off this derivative, you need to multiply by the derivative of the x plus 4, right? Okay. But that's so easy. What's the derivative of x plus 4? So when you differentiate this expression, yeah, it's just 1, right? So turns out to be kind of meaningless, right, Daniel? You just multiply in 1, but you can just sort of ignore. So we now have here minus 3/2, and because minus 1/2 times 3 is minus 3/2, and then x plus 4 to the minus 1/2 minus 1 is minus 3 halves. So we get the minus 3/2 in two places, right? Minus 1/2 minus 1 is minus 3/2. That's the first derivative, which is really kind of, we don't really care that much about the first derivative. Only we need that because we need the second derivative. So now we can go about finding the second derivative because we have an expression for the first derivative. And you're really going to just repeat the process now, right? You're going to bring down the minus 3/2 now. So minus 3/2 times this minus 3/2, and then x plus 4 to the, and you subtract 1 again. So you have minus 3/2 minus 1 here. And then don't forget to multiply the derivative of x plus 4, because this is not just x, it's x plus 4. So you have to multiply the derivative of x plus 4, but again, that's just 1. So that really doesn't make any difference at all in this case. So what does this second derivative end up looking like? Minus 3/2 times minus 3/2 is positive 9/4 times x plus 4 to the minus 5/2. Now let's simplify that a little bit. So that's 9/4 times 1 over x plus 4 to the positive 5/2. See that I can make that negative exponent positive by moving it into the denominator. And now let's rewrite that as a radical. So let's see, what is x plus 4 to the 5/2 power? Well, that's the square root, because this denominator of this fraction is 2. So you have the square root, and the 5 stays as an exponent. So you have the square root of x plus 4 to the 5th power. We could simplify that a little bit more, but it's really not necessary. So we have 9 over 4 times the square root of x plus 4 to the 5th power. Doesn't look that bad, okay? After we were finished with all of that, not that bad at all. Okay. Now we're going to evaluate that at 0. So I get 9 over 4 square root of 0 plus 4 to the 5th power. So I may have to have a calculator here, but maybe I don't. So we have 9 over 4 times the, that's a 4, So 4 times the square root of 4 to the 5th power. So you will need a calculator to help you with 4 to the 5th power. 4 to the 5th power, I think that is 1,024. Am I right on that? 4 to the 5th power? See if I can do that with, see if I
Yes.
can find this on my calculator even.
That's right.
Yeah, 1,024, right? You need the square root of that, which is 32. Okay, so you have 9 over 4 times 32. Whatever that turns out to be. I can see if I can take the reciprocal of that. Know that I can. So the calculator. So that's 9 over 128. And I think we need to round that off to a bunch of decimal places, right? So I get approximately 0.070. Actually, it's 3125. So that's what I think is the answer there for f double prime of 0. Is that what it say? Round your answer to 3 decimal places, right? So let's see if we can get that. See if we got that right. Got lucky. See if I can move over here. So 0.070. Hooray! So I get 1 out of 14. Yay! However many, oh, that's 6 points. Good. All right. So I've added to my very tiny average in the course with those 6 points. Does that make sense now?
That makes sense.
It always looks easy when someone else is doing it, right? So, but so you think you could duplicate that on the you think you could duplicate that on a test? So there are some questions like this on the sample test, and they are, in fact, let me see which ones they are. They're problem 9. So problem 9 from the sample test is finding a bunch of second derivatives. They don't ask you to, I don't ask you to evaluate those second derivatives. I just want the formula. An example like this would be 9D, okay? So 9D says that's finding a second derivative of a cube root, okay? And so that's kind of similar to, a little bit similar to this problem, okay? All right. So other things on there that you want to ask immediately from the homework? Okay, so well, we're gonna so remember that's due this evening, and we're going to and now we're going to continue looking at our, we're going to continue talking about implicit differentiation, which also relies on the chain rule, but in kind of a very indirect, manner. Okay.
I actually do have a question.
Yeah, Donna.
Can you do either the first or the second
The first or the second?
question? Yeah.
All right. So I think the purpose of this question was to try to get you thinking about sort of what two key functions are involved in this function y equal 3x minus 7 to the 7th power, right? Okay, so what they're asking you here, Donna, is what you really have here is an expression raised to a power, right? Okay, you have an expression raised to a power. And so what they're essentially what they want to know is what is the expression in this function? What is the expression that's raised to the power? And obviously it's what expression are you raising to the power here?
3x minus 7.
Yeah, so what goes in this slot? I didn't really teach the topic in this way, so this problem is a little bit not relevant to how we've been talking about the chain rule. So what they really want here is 3x minus 7. They're just trying to get you to see that to differentiate this function, you can use the power rule, right? But you have to keep in mind that the quantity that's raised to a power is not just x, it's the expression 3x minus 7. That's the point of this problem, which is kind of roundabout. Same thing here, okay? In this function, notice you have sign of quantity, right? Okay, but the quantity that you're taking sign of is not just plain x, all right? So what you really want to fill in is what is the quantity that you're computing the sign of, and it's 2x over 9, right? So I think here they just want you to fill in 2x over 9, just to think of, whoops. Yeah, okay. Just to emphasize that if you were to take the derivative of this function, you could do that by using the derivative of sine, which is cosine. So you would have cosine of 2x over 9, but then you would have to multiply in at the end the derivative of 2x over 9, which is 2/9. Okay.
Okay, that I thought it was a lot more complicated than that.
Yeah, no, it does look more complicated. The way they're asking it is very convoluted. Okay. So they want you to apply that sort of immediately in this problem, right? Where they ask you to find the derivative, and you just have to recognize, okay, I can use the power rule to find this derivative because I have, an expression raised to this power, right? Okay, so I can bring the 5 down and subtract 1 from the exponent. But then the only complication here is because this expression is not just x raised to a power, it's this function raised to a power. I have to, at the end, multiply in the derivative of 5 minus 9x. Okay, so your ultimate answer there would be, let's see, bring the 5 down and multiply by the 3. So 5 times 3 is 15, right? So we have 15, and then keep the 5 minus 9x. So you can keep the 5 minus 9x raised to now the 4th power, right? How do I get a 4th power out of this? Like this? Yeah, raised to the 4th power, because I subtract 1 from the exponent. But then at the end, we have to remember to multiply in the derivative of 5 minus 9x, right? Which is minus 9. So that expression inside the parentheses is easy to differentiate. Its derivative is minus 9. So at the end here, I have to remember to multiply in a minus 9. If you want to now, you could multiply the minus 9 times the 15, and that would give you minus 135. So you could write this as a minus 135, but this is also correct, okay? Just not quite simplified. Let's see we get credit for that if I submit that. Yeah, okay, so it still gave me credit for it. How come it won't let me? Oh, see if I did these two correct. Maybe I don't know what I'm talking about. Yeah, okay. So yeah, I think these are right also. Okay. All right, so other questions about the chain rule homework? Okay, so try to finish it by midnight. But remember, if you don't finish by midnight, you still have the opportunity to ask for an automatic extension, right? So you can continue working on it past midnight. Oh, Saad asking number 11. Is that like number 10? Kind of like number 10, right? We want to find the slope at this point, okay? We just have to find the derivative of 4x over square root of cosine times x. So that's a very unusual function. Probably in practice, you wouldn't encounter a function like that one, but that one is just sort of created so that you can get practice with differentiation, and in this case, with the chain rule. So we have to find the first derivative, and then once we found that, we have to plug in pi over 2 for x, right? Because we want to find the first derivative at pi over 2, which gives us the slope of the graph at this point. Probably that first derivative is going to involve some trigonometric functions, right? Which is why they have this unusual value for x, where they want us to evaluate this, right? So I imagine it's going to involve some sines or cosines, which would probably easy to evaluate at pi over 2, right? Well, the evaluation part we don't need to do, but let's look at the evaluation part we don't need to do, but let's do look at taking the derivative. So 4 over x plus cosine of x. That was the function 4 over x plus square root of cosine of x. And we want to find y prime. So Saad, important here first is, you want to rewrite your function formula in a correct form for finding derivatives. So the 4 over x, I would write that as 4 times x to the minus 1 power. Bring the x out of the denominator and write it with a negative exponent. The reason you want to do that, of course, is now to differentiate, you can use the power rule, right? You can bring the minus 1 down and subtract 1 from the exponent, right? If you try to differentiate it, leaving it as 4 over x, you would have to use the quotient rule to find the derivative of 4 over x. You can use the quotient rule to find the derivative of 4 over x. It works, but it's just going to be messy because you're going to have to remember the quotient rule properly, right? Okay. I think it's easier to rewrite it as 4 times x to the minus 1. Now, for the second term, well, the problem there is that square root, right? So you're going to have to write this as cosine of x to the 1/2 power. Okay. Now let's find the derivative. So just go turn by turn. Find the derivative of 4x to the minus 1 power. Bring the minus 1 down, so you get a minus 4. Minus 1 times 4 is minus 4, right? And then you have x to the minus 1 minus 1. That's going to be minus 2. Okay. And now the derivative of the second term. Well, that's going to involve the power rule again. So bring the 1/2 down. So you'll have 1/2 times cosine of x to the 1/2 minus 1, which will give you minus 1/2. So that's all easy enough. A little bit ugly, but it's easy enough to do that. But Saad, you have to remember to multiply in at the end what? So what's the catch here?
The derivative.
The derivative of what?
It's gonna be both, right? of the inside part.
Of the inside, right. So in other words, the derivative of cosine of x. But what's the derivative of cosine of x?
Negative sine x.
Yeah, it's minus sine of x, right? So that makes all the difference in the world. At the end, you have to multiply in the derivative of cosine of x, because you're not raising just x to a power, you're raising cosine of x to a power, right? Okay, so we have to multiply in the derivative of cosine of x. So we get this big messy expression here for the first derivative. Actually, though, at that point, you're really sort of done. You could plug in the pi over 2 at this point, and and simplify, okay? So, and you can do the calculations, you know, with x equal pi over 2, but we can clean this up a little bit. This is minus 4 times x to the minus 2 is minus 4 over x squared, so that's a little bit better. And then let's see, this minus sign, I'm going to move over here. Wow, what is all of this? So I have minus, and then this sine of x will stay in the numerator, but this 2 stays in the denominator, and this cosine of x to the minus 1/2, I'm going to pull that down to the denominator to make this exponent positive. So you still keep a 2 here. That 2 is in the denominator still, but the cosine of x to the minus 1/2 power, I'm going to pull that into the denominator. So I have cosine of x to the positive 1/2 power. But normally you wouldn't write 1/2 power any longer. You would convert this back to a square root. So you would have sine of x over 2 times the square root of sine x. So that would be sort of the simplified version of the formula for the derivative. And now you can plug in pi over 2 for x and get the numerical answer that they're looking for. I'm not going to do that, but you can do that. Okay, so now, you know, you get kind of an ugly expression for the derivative. Sometimes that happens. Okay, all right. So that's a good selection of problems. So keep working on that. Let's go back now to our implicit differentiation, and whoops, wrong one. And let's finish talking about those implicit differentiation examples. So remember, implicit differentiation is the process that we can use to apply derivative concepts to curves that are not functions. All right, so for several weeks here now, we've been just dealing exclusively with functions, curves that are functions. But at the beginning of the course, remember, we were working with sometimes with curves that were not functions, right? And here's an example of such a curve. So when you graph the solutions to this equation, really hard to do that by hand, but we saw the graph of the solutions to this equation last week. You get a picture that looks like this. All right, so it's a really cool looking curve. There's the equation over there on the left hand side, and you get a graph that looks like this. And so it's a nice curve, but it's not a function curve, right? Okay, because there are many x values on this curve that have more than one matching y value. 2 is a good example, right? If you use x equals 2, you get a y value up here, you get a y value of 0, that's 1 point on the curve, and then you get a matching y value down here. So see, this x has 3 different matching y values on this curve. And remember, you can't have that in a function. In a function, each x value has to have one and only one matching y value. So this is a nice curve, but it's not a function. But nevertheless, we can still find the slope of this curve at various points, well, really any point on the curve actually, by using a process called implicit differentiation. Okay, and so we can apply calculus concepts to curves that are not functions. That's really important, actually, historically, because calculus was used extensively, of course, in computing the orbits of planets, and the orbits of planets are not. If you trace out the orbit of a planet, that is not a function curve. Okay, that's an ellipse. And so planets travel around the sun in elliptical orbits, not circular orbits, but elliptical orbits, close to circles, but not quite. And ellipses are not functions, okay? But we still need to be able to apply calculus concepts to ellipses to help us compute these orbits. Okay, all right. So, well, I don't think there's an orbit of any object that looks like this. Okay, but nevertheless, we're gonna use implicit differentiation to help us find the slopes of this particular curve at various points. All right, so we actually went through last time the differentiation, the implicit differentiation process for this equation, right? So, and this is where we finished last time. We actually managed to find an expression for y prime, the derivative of y with respect to x, right? Okay, using this implicit differentiation process. And once we found this formula for y prime, then, you know, that's a formula for y prime, right? So we can use that to find the slopes of that curve at various places. Okay. Let's recall here really quickly that implicit differentiation process as we applied it to this equation. All right, and but we got some more examples coming up here also of implicit differentiation. All right, so what we're going to do now, remember, is go term by term and find the derivative of every term in this equation. But remember, we want to take the derivative with respect to x. So we're thinking of x as being the input variable and y as being the output variable. So remember, the variable we're differentiating with respect to is x. We're finding y prime, which is dy dx. All right. So x is the main variable here. Y is the output variable. All right. So so how do I go through this implicit differentiation process? All right. Well, again, you're going to differentiate every term in the equation on both sides of the equation. So it's easy to differentiate -4 with respect to x because that is a constant. So when you take the derivative of -4, you get just exactly like you would expect, you would get 0. Okay. Likewise, let's look at this term. I'm not going from left to right here, but you can go from left to right, but I'm just going slightly out of order here. When you differentiate, so when you differentiate -4, you get 0. When you differentiate minus x squared, you get, again, exactly what you would expect, right? You know what the derivative of minus x squared is, correct? You bring down the 2, and that would give you then a -2, and then subtract 1 from the exponent. So that gives you -2x, okay? So the derivative of minus x squared is just like you would expect it would be -2x. Where things are going to get a little bit complicated, okay, is when you're differentiating things like y cubed, all right? This is where the chain rule is going to come into play, all right? So to differentiate y cubed, as we saw last time, you're still going to use the power rule. So bring the 3 down and subtract 1 from the exponent. So you get 3 times y squared. The thing to remember, though, is that you're differentiating with respect to x, okay? So you have to finish the derivative of this term by multiplying in the derivative of y, okay? Now, that's a little bit confusing, right? What is the derivative of y with respect to x? Well, we don't quite know what the derivative of y with respect to x is. So we're just going to write down our symbolic name for the derivative of y with respect to x, which remember is y prime, all right? So when you differentiate when you differentiate y cubed, you get 3 times y squared. You're just going to use the power rule just like you would expect. But then at the end, you have to remember to multiply in the derivative of y. You can write that as y prime, or you can write that as dy over dx. I think it's easier to write it as y prime, but if you want to, you can write it as dy over dx. Okay, that is the chain rule coming into play here, okay? The reason the chain rule comes into play is because y is not the input variable here. Y is the output variable. X is the input variable. So when you differentiate y cubed, the chain rule is going to be required here to carry out the differentiation properly. So how do we differentiate y squared? Same thing. Just use the power rule. Bring down the 2, subtract 1 from the exponent. So you get 2 times y, just like you would expect. But then at the end, you have to multiply in the derivative of y, which is y prime. And what's the derivative of minus 5y? Well, again, you can use the power rule again. Bring down the 1, so you get 1 times minus 5. And then multiply in the derivative of y, which is y prime. So there you get this big, long equation. Notice it's still an equation because you differentiated both sides of the equation. Now you just solve that equation for y prime. So what you have to do, as we did last time, is you want to gather all the terms that involve y prime. That would be this term, and this term. Gather them on one side of the equation, and all the terms that don't involve y prime, which in this case is the minus 2x, bring that to the other side of the equation. So what I did here was move the minus 2x back over to the right, because that term doesn't involve y prime. Then all these terms on the left still have y prime in them. So I factored out y prime from all of these terms. So I factored y prime out here, y prime out here, y prime out here. That gave me y prime times 3y squared plus 2y minus 5. And then I divided by the 3y squared plus 2y minus 5 on both sides of the equation. So when you divide by the 3y squared plus 2y minus 5 on both sides, well, on the left-hand side, it cancels. So you just get left with y prime. And on the right-hand side, you get this, well, kind of ugly formula, right? 2x over 3y squared plus 2y minus 5. And that is the formula that we're going to use for the derivative. So what's a little bit unusual about this formula for the derivative and formulas for derivative we've seen in earlier examples is, notice this formula for the derivative involves both x and y. It doesn't involve just x, okay? So you have to keep that in mind. If you're going to evaluate this formula for the derivative, you have to have a value for x and you have to have a value for y. So if you don't have a value for both x and y, you're really not going to be able to use this derivative formula. All right, well, let's actually apply this derivative formula now and see what we're asked to do with it. So it says, find the equation of the tangent line. Find the equation of the tangent line to this curve. That was the curve that I showed you at this point, 1 minus 3. Let's look at that curve again and see what we think that, let's look at this curve again and see what we think that tangent line looks like. So we want to find the equation for the tangent line to this curve at the point 1 and minus 3. So there's x equals 1. And down here, oh, there it is. Is that the point? Yeah, there it is. Okay. So there's the point. Hard for me to point at it perfectly. I didn't get it there. I had it there a moment ago. But right here on this curve is the point. Oh, there it is the point 1 and negative 3. So that point is on the curve. And we want to find the equation for the tangent line right at that point. So can you imagine what that tangent line is going to look like that touches that point on the curve? Is that tangent line going to have positive slope or negative slope? What do you guys think? Right there at that point, if you drew a tangent line to that curve at that point, would it have positive slope or would it have negative slope or would it be flat?
Positive.
Yeah, Saad, I think it's positive. It's just very slightly positive, right? Okay. because yeah, if you draw the tangent line right here, unfortunately I can't draw it, but if you draw the tangent line right there at 1 minus 3, it's going to have just a little bit upward slope, right? The curve right there is increasing just very slightly from left to right, okay? So I think it's going to have a really tiny positive slope. Not 0. I think this point would have, the tangent line would have slope 0, right? Okay, but not right here at 1. I think it's a little bit positive. Well, so let's see what it is exactly. Okay, so so what would be the slope of the tangent line right there at the point 1 minus 3? This is where the derivative is going to be useful to you. Okay, so you want to evaluate this derivative at the point 1 minus 3. Okay, so that means you're going to plug in x equal 1 and y equal minus 3 right into this formula. But that's all you have to do. So we have 2 times 1 and then 3 times a minus 3 squared plus 2 times a minus 3 minus 5. And then just do that arithmetic. Let's see, what does that end up looking like? That's 2 over 3 times minus 3 squared. I think that's 27 minus 6, 2 times minus 3 minus 5. So it looks like it comes out to be 2 over, what is that, 16, which is 1/8. So see, that is a positive number, not a very big positive number, right? So we do have just a little tiny positive slope there, right at this point, 1 minus 3, just like we expected it would be. And let's see, so the slope is 1/8. What's the equation for that line then? Well, that's easy. It's going to be y equals 1/8, because that's the slope, right? X minus 1, because the tangent line has to go through this point, and then add on the y coordinate. So there's the actual equation for the tangent line. Hey, let's try an experiment here. Let's go back to Desmos and here, and let's actually type in that formula. So it was, see if I can find my keyboard here. So see, that formula was what? Y equals 1/8 what was that? X minus 1 and then what? Minus 3?
Yeah, minus 3.
All right, so now let's move all this stuff out of the way and take a look at and see if that does that look like the tangent line? Yeah, I think it is, right there at this point. There it is. Yeah, it looks like we graphed the right tangent line there, right? So I think we got it. I think we got it exactly correct there. Okay, just from examining it. Let's look at the other questions here. They're kind of interesting also. We talked a little bit about these last time. So the next part of this one says, same curve now, find the points on the curve where the tangent line is vertical. So find the points on the curve where the tangent line is vertical. So you can see those pretty easily in the graph, right? This point, that's 1, 1, is going to have a vertical tangent line. If you think about what the tangent line looks like, you're going to get a vertical tangent line right here, right? And then also right there, at that point, if you draw the tangent line, it's going to turn out to be vertical. We haven't often talked about vertical tangent lines in this class, but curves can have vertical tangent lines. you know, we've been kind of obsessed with horizontal tangent lines, but curves can have vertical tangent lines as well. And so there's a point also that's going to have a vertical tangent line if you draw the tangent line. And this point on the other side, this symmetric point on the other side, will also have a vertical tangent line. And this point also will have a vertical tangent line. My word, how are we going to find, you know, I can see them on the graph, but how are we going to find it with pencil and paper where these points have vertical tangent lines? Let's go back and look at our formula for the derivative. Okay, so we have this formula, remember, for the derivative. And what do you know about the slopes of vertical lines? Vertical lines,
It's
not horizontal lines. Horizontal lines have slope 0. But what about the slopes of vertical lines? So if you have a straight up and down line, what is its slope? Someone know that? Slope of a vertical line.
Undefined.
Undefined, yeah, Alva, great. Yeah, Alva, that's right. Thanks for answering. I was gonna ask you a question today anyway. So wow, you got checked off there easy. Yeah, so slopes of vertical lines are undefined, Alva. Okay, so if we look at our derivative expression, we remember that's going to give us the slope of the tangent line. So we want this, we want to figure out where is this formula going to be undefined. Okay, that's what we're trying to discover. Where is that formula going to be undefined? But that formula is a fraction. And where are fractions undefined? When will a fraction?
Whenever the
go ahead,
denominator equals 0.
Yeah, whenever the denominators equal 0, right? Okay, so our you know, our little bit of detective work here tells us that, oh, what I'm interested in knowing is where is this denominator going to be 0? Okay, because that's going to make this fraction 0, and so that's going to give me a derivative or a slope which is undefined. Okay, so that's really what we're looking for here, is where is the bottom of that fraction, the denominator of that fraction, going to be 0? Well, so we can figure that out because that just means we have to solve an equation. So let's take the denominator of that fraction, 3y squared plus 2y minus 5, and we'll just set that equal to 0. So we have 3y squared plus 2y minus 5, and we try to solve this equation. Okay, so that's a quadratic equation because the y is squared, and my methods for solving quadratic equations involve the quadratic formula, but I'd like to avoid the quadratic formula better if I can just factor. So does this thing factor 3y squared plus 2y minus 5? Fortunately, these are all prime numbers, so if it's going to factor, we don't have that many options. We're going to have a 3y and a y if we're going to get 3y squared, right? And to get a 5, we're going to have a 1 and a 5. So is there someplace I can put a 1 and a 5 here that will give me the correct middle term when I multiply back together? I think so, right? Can't I put the 5 here and the 1 here and make this positive and this one negative? Does that work? Let's see, 3y times y is 3y squared, plus 5 times minus 1 is minus 5. That's nice, okay? And now let's see, what about for the middle term? You would have 3y times minus 1 is minus 3y, and then 5y is positive 5y. Well, positive 5y and a minus 3y is a positive 2y. Yay! So there is the correct factor. What a luck, okay? So this equation factors, and so that means I'm going to be able to get the solutions really easily without having to use that ugly quadratic formula. So I have 3y plus 5 equals 0, which means y is equal to minus 5/3. Neat. Or y is equal to 1. So that tells us that on the curve, we know there are going to be points with vertical tangent lines where y is minus 5/3. So I think that's this point and this point, right? Because both of those points have y coordinate minus 5/3. Minus 1.667 is minus 5/3, by the way. Okay, so these 2 points will have vertical tangent lines, and these 2 points, notice their y coordinate is 1. Okay, so what we found on pencil and paper here is exactly correct, right? We know we have a vertical tangent line where the y is minus 5/3, and we have a vertical tangent line where the y is 1. So points like this will give us on the curve, we'll have vertical tangent lines. Now, what about the x coordinates? So how would I find those? Because I know the y coordinates have to be 1 and minus 5/3. How would I find the matching x coordinates here? So how would you fill in this? Yeah, go ahead.
Can you substitute the y value for one of those values and then solve
Yeah,
for x?
substitute the y value where, Colin?
I'm not sure.
Well, don't go back here, okay? All right, because when you don't go back to the derivative, because when you substitute either of your y values into this derivative, you get a 0 denominator. So that's not helpful, right? Okay, so you have to go all the way back to the original formula. Go all the way back to the original formula, this formula, and plug in those y values that you got, minus 5/3 and 1, and find what the matching x values were. Let's try the 1. The minus 5/3 is a little bit messier, but let's try the y equals 1, okay? Just to show you the process, because that was one of the y coordinates, right, where we had a vertical tangent line. So I'm going to plug 1 in for y here. Don't plug it in for x. Remember, the 1 was the y value. So you have 1 cubed plus 1 squared minus 5 times 1 minus x squared. I don't know the x. That's what I'm looking for, equals minus 4. Let's see, what's this? This is 1 plus 1 minus 5 minus x squared equal minus 4. So that looks like minus 3. 2 minus 5 is minus 3. Minus x squared equal minus 4. And now if you rearrange the terms here a little bit, you end up with x squared equals 1. Nice. And what's the solution to that equation? X squared equals 1. I think that means x has to be what?
Plus or minus 1, right?
Plus or minus 1, right? Yeah, don't forget there's 2 solutions there. X is plus or minus 1. Oh, so there we have it. There are 2 of the points where we have vertical tangents. X can be 1, y is 1, and x can be minus 1, and y also is 1. Now, to find the other 2 points, there are 2 other points. Both of them have y coordinate minus 5/3. Plug the minus 5/3 in for y back in your original formula and solve for x, okay? You're going to get some messy x value. If you look on the graph, we can sort of figure out what it is. Apparently, it's going to be something like minus 3.238 and positive 3.238. Okay, so you get 2 x values there to give you these other 2 points where you have vertical tangents. Let's try the last part here, since y'all. Oh, well, that was the last part. Okay, so. Nice. All right. Well, okay. So, well, we better take a quick break. All right, and then I'm going to come back and let you. I'm going to come back and let you try one. Here's the one I'm going to let you try. So, this also is a when you graph this curve, you don't get a function. You get a nice graph. I think this is just a circle, and maybe it's not a circle or an ellipse. Okay, so something like that. So but not a function. But still, we can find the tangent lines to this curve. at various points. And 1 point on the graph of this, 1 point on the graph of this equation is this point, square root of 2 and minus 1 over the square root of 2. So we want to find what's the slope of the tangent line at this point on the curve. Okay. All right. So, but we'll try that one using implicit differentiation again when we get back. So let's take 5 or 6 minutes here and catch our breath, and then look at this problem. All right. So I'll see y'all again in 5 or 6 minutes. Okay. Oops, let me pause the. Okay, we're back, and I'm going to give you a problem, the one I mentioned here before the break there, right? So, so this is example 4, and we want to determine the slope of this of the tangent line to this curve at this point. It turns out this point is on this curve, square root of 2, and then minus 1 over the square root of 2. Actually, I've got a graph of this one, so let's take a look at what we're doing here. So I think it's this one. Oh yeah, so I'm right. It was an ellipse. Looks really skinny here. We can blow it up, but yeah. So x squared plus 4y squared, you just get this nice nice ellipse. Okay. And square root of 2 would be somewhere about right here on the x-axis. So these 2 points above here on the top and here on the bottom, these are roughly the points have x coordinate square root of 2. And so I think we're looking for the slope of the tangent line at this bottom point in this problem. Okay. All right. So so there's kind of a picture of what it is that we're doing, but we don't really need the picture, right? We can do all of this just with calculus and on pencil and paper, right? Okay. So so the first step of this process is to and really the key step here is to find an expression for the derivative, right? So you're going to be looking for, you can denote it as y prime, or you can denote it as dy over dx. Both of those are useful in different situations. Okay, I think it's easier to work with y prime. All right, but again, both of these notations are useful in different situations. So you're just trying to find a formula for y prime using that implicit differentiation process, right? So remember, that process is you look at your equation for your curve, you differentiate both sides of the equation, left and right, you go term by term. So just differentiate, you know, from left to right here, term by term, each of the terms. And then when you've done that, solve the resulting equation that you get. You'll still get an equation when you differentiate both sides of the original equation. Solve that resulting equation for this variable y prime, right? Okay, and that will give you a formula for the derivative that you can use to find things like slopes of tangent lines at particular points. All right, so so I want you to try that one. Just start with, don't worry about the slope so much. Just start with, see if you can find a formula for the derivative using implicit differentiation. And actually, we can stop at kind of an intermediate point, see if you can just differentiate both sides of the equation without even trying to solve for the y prime. See if you can differentiate both sides of this equation first. Okay, if you can do that, then usually the rest of it is pretty straightforward. Okay, all right. So try that first. And let's just take a couple of minutes, and then we'll come back and look and see what people got. All right, for that. So we don't want to take too long. If you don't get through all of the parts of differentiating both sides of the equation, that's fine. We can just fill in those pieces, as we go. So I'm going to ask someone to share. So you've all been so good about sharing all semester. Okay, so let's just see if we got something here. All right, that we can work with. So Luis Ruiz, let me ask you first. Okay, Luis, are you there?
Yes.
All right. So can you tell me how you would start this?
You get
Go ahead.
you multiply 2x.
Yeah, so you would start with 2x, right? That's just the derivative of x squared, right? So you would just get 2x. So that's all very straightforward, right? Okay. The derivative of x squared is 2x. Now, what about the 4y squared?
You do the same thing. You multiply by 2, 4.
Yeah. So you would get bring the 2 down times the 4, so you would get 8, right? And then y to the first power, right, Lewis? But here's the tricky part, correct? Because what else do you have to add to this term?
The y derivative.
That's right, y prime, right? The derivative of y. That is the chain rule. So the chain rule comes into play in this term because it involves y, right? So you get 8 times y times y prime. And then, this is easy now, Lewis. What's the derivative of 4?
0.
0, right? So you end up with this really a nice equation here, right? Okay, and now all we have to do is solve this equation for y prime. Oh, well, okay, Lewis. So since you got off to a good start there, so how do I solve this for y prime?
You move the 2x to the right.
Move the 2x to the right, and so you get 8y prime equal minus 2x, right? And then what's left? Not much, right?
8y.
Yeah, divide both sides by 8y. Yeah, perfect. And so we just get y prime is equal to, I guess, minus 2 over 4 reduces to 1/4, right? So we would have minus x over 4y. Yay, okay, so really pretty straightforward, right? So there's the formula for the derivative y prime. And now to find the slope of the tangent line at this point, this is all just easy, right? You're just going to evaluate this at x equal square root of 2, and then y equal -1 over square root of 2. So you just plug those values into this formula. Wow, what is that? What happens there? So you get minus square root of 2 over 4 times -1 over square root of 2. Wow, what's all of that? Looks awful. I guess these minus signs are going to cancel ultimately, so we can get rid of those. So it looks like we have square root of 2 over 4 over square root of 2. Because I just multiplied the 4 into the 1 over square root of 2 in the bottom. And let's see, so this is square root of 2 times the square root of 2 over 4, because I'm just going to invert this fraction and multiply. When you divide by a fraction, that's the same as inverting the fraction and multiplying. So this is the same as taking square root of 2 and multiplying it by square root of 2 over 4. But square root of 2 times the square root of 2, that's 2. So we have 2 over 4, which is 1/2. So we end up getting a pretty nice slope there after, takes a little bit of work, right? But it all just comes out to be 1/2. So the slope of the tangent line at this point is about 1/2. Remember, that point is somewhere down here. See if we can find that. We want square root of 2. That's about right there. So roughly right there is square root of is when x is equal square root of 2. Square root of 2 is 1.414. So that's so we're looking for the slope right at about that point. Yeah, 1/2 looks like that could be it, right? Okay. If we just imagine what that tangent line is going to look like. Okay. All right, I want to quickly do the, there's another example here. We're not going to do all the parts of, this last example because we sort of run out of time, but let me here quickly just do the key parts. So what the question actually wanted was find the slope of this curve at this point, 3, 1. So it turns out this point, 3, 1 is on this curve. If you plug 3 in for x, you'll ultimately discover that y is 1. Let me show you what that curve looks like just for fun. I think it's this one. Oh, yeah, so you have a beautiful figure 8 curve here, right? Okay, and apparently the point 1 through, oh yeah, this point right there is on that curve. That's 1, 3. Okay. All right. So so there's the curve that we're working with. I just want to show you how to find the. I just want to show you there how to find the. Go through the implicit differentiation process here with you. Okay, because this one is a much more complicated. This is a much more complicated formula than the other 2 examples. All right, so let's go through that implicit differentiation process. All right, so let's start by differentiating the left-hand side here. Okay, so 3 times x squared plus y squared squared. Anybody have a suggestion of where we would start differentiating that? What does it look like you're gonna? What does it look like you're gonna do there?
Bring the exponent 2 down.
Yeah, right. And that's the first thing that I would think about, right, Donna, is looks like the power rule is going to be involved here, correct? So bring the 2 down. So you would have 2 times 3 times x squared plus y squared. And then all that's left of your exponent is 1. So that's nice. But then, Donna, we always have to remember, since we're not raising just x to this power, right? We're raising this expression to the power. What do I have to multiply in here?
Is it y prime because there's a y involved?
Yeah, well, it's the derivative of this. So we have to think about the derivative of x squared plus y squared, okay? So let's see if we can do the derivative of x squared plus y squared. Well, just take it one, so just the part in parentheses, just take it one term at a time. So what's the derivative of x squared?
2x.
That's easy, 2x. And now what's the derivative of y squared?
2y.
2y, but you have to throw in what other factor?
Y prime.
Y prime, right? That's the thing you always have to remember, okay? Because y is considered the output variable here. Y is a function of x. So you take 2x plus 2y, y prime. That's the derivative of what's inside the parentheses. Well, that's it though, okay? So there's the left-hand side differentiated. Now on the right-hand side, let's see. I have to differentiate 100x times y. That doesn't look that bad, except you have to keep in mind there's a product here. You have 100x, that quantity times y, okay? So there's a product involved. So to differentiate the right-hand side, you're going to have to use the product rule. All right, so let's do that. So I have 100x is one factor, y is the 100x is the first factor, y is the second factor. So what does the product rule say? It says, you take the derivative of the 100x first. What's the derivative of 100x?
100.
100. And then you multiply by the y, keep the y, okay? Then add on, keep the 100x, and then multiply by the derivative of y. But we don't know what the derivative of y is, but we're just going to call it what?
Y prime.
Y prime, right, okay? So just multiply there by y prime. And there you got it. Now, of course, there's a lot more work here to do because now we would have to take this equation and solve it for what?
One, 3.
Yeah, what side? What do we want to solve for in this equation?
You want to solve for 3 in respect to x?
But no, we've already differentiated, right? Okay. So we differentiated both sides. That's what Donna helped us with. And now we have to get what? What do we have to isolate out of this equation?
Y prime.
The y prime.
The y prime, right? Okay. So you have to solve this equation for the y prime. Let's see. Wow. Okay. That's easier said than done. So what you would have to do is expand this product on the, so this is going to be a little bit messy. We have to expand this product on the left-hand side, okay? So let me see if I can do that. So I have 6, this is 6, right? So I have 6 times x squared plus y squared times 2x plus 2y y prime. Let's multiply all these things together now. All right, so let's distribute here. So we have 6 x squared times 2x. So I'm going to multiply the parentheses together first. X squared times 2x, that's 2x cubed, right? X squared times this would be 2x squared y prime. Now y squared. Y squared times 2x, that's 2x y squared. And y squared times this term is 2y squared times y is y cubed times y prime. Don't forget 6 is multiplied by all of this, though. Well, let's multiply the 6 in. So I have 12x cubed plus 12x squared y prime plus 2xy squared. Whoops, I forgot multiply my 6 in, so that's 12. And then plus 12 y cubed y prime. All right, so we expanded all of that. We expanded all of this product here on the left-hand side. So you end up with what looks like a mess. But what are you going to do with all of these terms that you have in this equation? What's our goal at this point? Assuming that we got through this algebra correctly, right? Okay, what are we going to do at this point?
Still have to solve for y prime.
We still have to solve for y prime side. So how do you solve for y prime here, though? So what are you going to do with all these terms to solve for y prime?
You could divide the term on both sides.
Wait, I'm not sure I understand what you're saying. You can do what?
So, okay, for the first term, you could subtract 12 x to the power of 3, bring it to the other side.
You're going to bring it to the other side?
Oh, I was thinking I was going to bring all the y prime to the left and all the x to the right. And
That's
then,
what I wanted you to say. Yeah, right. Okay, that's correct, right? You want to bring all of your y prime terms to one side and all of the other terms to the other side. Okay, so I think you were just explaining that process to me, but we can do that very quickly. Let's see, here's a y prime term, so we'll keep that. So we have 12x squared y prime, right? So I'm keeping that one. That one's kept, right? I'm going to keep this one on this side, right? So I have plus 12 y cubed y prime, right? So I kept that. And this term now, I need to get that back over to the left, right? So we'll just move that over to the left and the sign changes, right? So we end up with 12x squared y prime plus 12y cubed y prime minus 100xy prime. I'm going to keep that on the left. And then the other terms, I'm going to move them to the right. So it looks like the 12x cubed is going to go to the right, correct? That becomes negative, though. Got to be very careful about my signs. And then this term is going to move to the right, so it becomes negative. So I have 12xy squared, right? Okay. And then this term is left over here on the right-hand side, right? So there's 100y. All right, so I think I've got all my terms accounted for, right? Oop, do I have them all accounted for? Am I missing one? Did I forget one here? Have I lost track of a term? 12, this one, 1, 2, 3, 4, 5, 6. Oh, yeah, I've got them. Okay. All right. Now, so we've separated the y prime terms, right? Now, what's almost done, right? Now, from the left-hand side, factor out the y prime. So you get y prime times the 12x squared plus 12x squared y plus 12y cubed, factored out the y prime, minus 100x, because I factored out the y prime, equals to all of this stuff on the right-hand side. And now all you have to finish here is divide by what's in the parentheses. Whew, gosh, what a terrible problem. So we end up with minus 12x cubed minus 12x y squared plus 100y over 12x squared y plus the 12y cubed minus the 100x. Yeah, okay. Oh, that's a nice practice with algebra. All right. So a big expression for the derivative. Okay. All right. So and then if you want to find the slope at the 0.31, you just have to do arithmetic, plug 3 in for x and 1 in for y, and simplify that arithmetic, and then you can find the slope of that nice figure 8 curve at that point 1, 3. Okay. All right. So, well, there's our last examples with implicit differentiation. All right. So that's the last part that's on the test. I don't think the implicit differentiations on the problems on the sample or test are nearly as complicated as this one, though. All right. So I'm not sure about the homework, but I think that's probably more. That last problem is probably more complicated than you'll see on the test or on the homework. All right, so well, we're done for today, so we've run out of time. So next time we're going to revisit a topic that so we're going to stop differentiating for just a moment, and we're going to revisit an earlier topic that we had used in helping us differentiate. But we want to go back and revisit that topic a little bit more closely because it has more importance later in calculus. That's the topic of computing limits. Okay, so remember we had to compute limits when we were finding derivative functions, but we actually have to compute limits of other types of expressions frequently in calculus. So we're going to look at that topic a little bit more in depth next time. Okay. All right. So I will see y'all then. All right. So be sure to finish your chain rule homework for this evening. All right. And I'll see you guys on Thursday. And be studying for your test now. Remember, I'm going to post the solutions sometime tomorrow. The solutions to the sample test will show up in the will show up on Blackboard. Okay. All right.
Professor,
Yes.
I had one more question on the chain rule homework.
Oh, okay. All right. So yeah. So I'll go over that one. Yeah, y'all can stick around if y'all want to see this one. I'm going to stop the recording though. So, and we'll talk about that.